Chapter 4. It says dynamics, forces, and Newton's laws. I think that's what the name of it is. Chapter summary for the OpenStax College Physics textbook, Chapter 4. Spoiler alert, this chapter is about this equation. This says that the net force is mass times acceleration. That's the big deal. And it's a vector, and it's the sum of the vectors, and that's a vector. We've already looked at acceleration before. But really, this is a way to describe interactions. So let's talk about interactions. So here's just a piece of paper, right? And I can hit it with my hand. And how do I describe this interaction between my hand and the object? And we use this idea of forces to describe interactions. That's what this is all about. Describing interactions from the perspective of force. Now, there is another way to describe interactions. We don't have to use just forces. And we'll talk about that later when we look at the work energy principle. But right now, forces is a way for us to give perspective on reality and describe interactions between objects. Okay, let's start off with force. So we have force. It's a vector. We've talked about vectors before, so it has 3 dimensions. It has units of newtons, so 1 newton is equal to 1 kilogram meter per second squared. And, a lot of people say, oh, it's a push or a pull, but that's not wrong. We're going to talk about the properties of forces, but that's what it is. Now, I do think it's useful to talk about how do we measure forces. This is a spring scale, and we're going to look at springs later. But the really cool thing is that it turns out that the more you stretch that spring, the greater the force exerted on this. So in fact, I could go the other way. I could pull on it a certain amount, and by measuring the distance it gets pulled, I could determine this force. And this scale has units of newtons on there. Zoom. Okay, so this is called a spring scale. Very useful, very simple thing. You could replace that with a rubber band. It would mostly work. You could build your own spring scale. Now, there's another way to measure force. Here is a digital scale, and that's upside down. And so in this case, I can pull on the hook or push it, and it can read a force in newtons. Now, this works by there's 2 primary ways you can make a force device like this. One way is with what's called a strain gauge, and basically you have a series of resistors, and when you pull it, the resistance changes. By measuring the change in the resistance, you can determine the force. And the other way is probably the way this works is with a piezoelectric device. So some crystals, when you squeeze them, they produce a voltage. You record the voltage, you calibrate it, and you get the force. And we don't really need to know that, but it's kind of fun to know, right? Okay, so that's how we measure forces. So we can indeed measure forces. Now, let's take a break and talk about the first person, I need my eraser, to look at forces. Really, maybe not the first, but the person that we have a lot of recordings from to look at, or writings from, and that's Aristotle, the Greek philosopher. Because Aristotle, first of all, the Greeks had a deductive way of thinking. So what they would do, I like this triangle, is to take some idea and then deduce all the facts that they could get from that. And that's the way Sherlock Holmes is a deductive reasoning. This is deductive reasoning. So it says, here's something that we all assume to be true. These are all the things we can work out. I can take the idea that we all assume to be true, that rocks fall, and that heavier rocks fall faster, which isn't true, but it seems like it'd be true. And then we can deduce all these ideas from that. Okay, so we now do inductive reasoning. Data, idea. So we take a whole bunch of pieces of data, like we can measure the speed of a falling rock. We can change the mass and make an experiment. And from all that data, come up with an idea. And that's what we do in science. This is what they do in philosophy. And from that, Aristotle had four, he wanted to look at how objects move. And first he had this idea of natural motion. So we have these things. That's fire. We have this one, air. We have this one, rock, water. And he said that everything is made up of these, and they want to do what they want to do. So rocks and water want to go to the earth. They go down. Air does whatever it wants to. I don't really know, but fire rises. Okay, so this is why a rock falls. A rock or any object would fall. I'll take this paper because it's light. It falls because it wants to get to its natural position. Natural position. Furthermore, if I take an object, its natural position is at rest. This is really important here. If you leave it alone, stopped. Okay, that's what that says. The natural position is at rest. If I push on it, if I exert a force, if I interact with it, then that's a violent motion. That means I'm going to make it do what it doesn't want to do. So I'm going to take it away from its natural rest, natural motion, which is at rest, and it will move. And when I stop being violent to that object, it stops. And that just makes sense, right? Everyone can agree. If I push that object, it'll move. When I stop pushing it, it stops. Aristotle seemed to be right. This idea lasted for 1,000 years or more. Everyone said, well, Aristotle says. Okay. And these ideas still persist today. Many people will say, well, if you don't push on an object, it stops. Therefore, if there's a force on it, it will move. If there's no force, it will not move. Many, many, many people say that. It comes up many, many times. It's very popular. Aristotle made a lot of sense, but he did not do an experiment. Next, let's look at another person. And this is probably not even a true story, but this is the Leaning Tower of Pisa and Galileo. Did I spell that right? And so the Leaning Tower of Pisa says that Galileo dropped objects of different mass and showed that they fell at the same time. He was from Pisa, that's for sure. And it may have actually happened. It may have just been a thought experiment. I don't know. He didn't post to his Instagram feed what was actually happening, so I don't know. Or his account got deleted. I don't know. But that was one thing that was attributed to him. But this is an experiment that you could do. But the more important experiment, he did the following. And this is a really nice experiment. So Aristotle said that if you drop an object, it will move down at a constant speed. So what Galileo did was to take a ramp like this in a ball, and then he would let it go for 1 second. And it's a very, very long time. You can time 1 second with a number of devices, a water clock that drips drops. You could time it with a sand clock. It's not too hard to do. And so in 1 second, it may move that far. That's 1 second. Now, after the second, so after another second, it may move that far. After the third second, it may move that far. So this distance divided by that time, this distance divided by that time, this distance divided by that time, it's not moving at a constant speed. It's increasing in speed. It moves further and further and further each time. And he said, hey, maybe that's the same thing that happens with a falling object. It just happens a lot quicker. Because you can take this ramp, and as you increase it, the speed increases more. But he found something else very important. Suppose you take a track that's just barely inclined, and you take a ball and you give it a little push. It will move at a constant velocity, constant speed. Okay? And so this is because at that angle, at a very small angle, the frictional force and the gravitational force that makes it roll down are balanced. But he idealizes to say, well, in an ideal situation, if I have no forces acting on this object, this could move with a constant speed. that's important because that's not what Aristotle said. Aristotle said that if you don't push it, it's going to stop. And Galileo said, well, I got it to almost move without an interaction. And I imagined that if I had a perfect situation, it would move and it would not stop. So we've gone to this thing about what is the natural state of motion. Aristotle says it's at rest. Galileo says, aha, maybe not so much true. And now let's get to the third person in our little story here, Newton. So Newton took the ideas of Galileo and kind of formalized them. And we get to, I'm going to go through Newton's 3 laws of motion. So Newton's first law of motion. And I don't think you need to memorize these. Newton's first. I'm going to write this the way I like it. Aristotle is wrong, or was wrong. That's what Newton's first law says. It says that Aristotle was not right. Aristotle said that the natural state of motion, if you do not push on something, it will be at rest. Newton says the natural state of motion is to not change its speed. So you'll see it not change. And let's say velocity as a vector. He didn't say it as a vector, but we're saying it as a vector. So, you may see this as if there's no interaction on a force, it'll move at a constant speed in a constant direction. That's one way to say Newton's first law. It kind of is redundant with Newton's second law because it's really about, hey, everyone out there, that guy Aristotle, he was wrong. Which was a big deal because everyone really liked Aristotle. Okay, so that's what Newton's first law says. Some people say it's the law of inertia. And that's fine. Inertia just says what's its resistance to change in motion, and it depends on the mass. It's proportional to the mass, and in fact, inertia is mass. Okay, Newton's first law. Newton's second law, I don't have to erase everything. It's second. So imagine that I push on this block, and it accelerates. If I push with a greater force, it has a greater acceleration. If I push on it with the force and it accelerates, and then I increase the mass, it has this lower acceleration. So he says that the acceleration is proportional to the force. The acceleration is inversely proportional to the mass. And so from this we get Newton's second law, F net equals mass times acceleration. Now, that is there's two things that people get wrong here. The two things are, one, it's a vector equation. All right, so you have to put the vector over force, the vector over the acceleration. Mass is not a vector. And number two, net. Okay, it's the net force. If you see someone just says, oh, fun, haha, I'm a cool physicist, F equals ma. No, that's not really good. It's not a vector equation. It doesn't have net force. So this says that the total force, the sum of the vector forces acting on an object, is equal to the mass times the acceleration of that object. If I have a block, I push on it with F1, I push on it with F2, then I can say F1 plus F2. I have to add them as vectors, and we're going to do that, is mass times acceleration. That's what Newton's second law says. Okay, third law. But just remember, we're trying to describe interactions using force. This says that if I have two objects, A and B, and they are interacting, then B will push on A during this interaction, and it'll be like this. I'm going to write this as FB dash A. So this is the force, the vector force of B pushing on A. Well, A also pushes on B this way. So I can say the force of A pushing on B. That's just the notation I like to use. And Newton's third law says that FA on B is negative FB on A. Or you could say forces come in pairs. Or you could say forces are always an interaction between two objects. There has to be two objects for there to be a force, and those objects interact. If I push on the board pushes back on me. If the earth pulls down on me, I pull up on the earth. Equal and opposite forces. That's what that says. Now, we have a version of this that's useful in distance. So suppose that I have, let's use, let's say here's the United States. That's the United States. And here's LA. And this is, let's say, Jacksonville. And let's say it's 3,000 miles. I don't even know. 3,000 miles. So if I go from LA to Jacksonville, then that would be 3,000 miles east. If I go from Jacksonville to LA, that would be 3,000 miles west. And in fact, we can talk about the distance between Jacksonville and LA is 3,000 miles. If you go from LA to Jacksonville, it's east. Jacksonville to LA is west. And those are equal and opposite distances. The distance between two objects have equal and opposite distances. It's the same thing. Same thing with forces. The interaction between two things we can measure as a force, and they're going to be equal and opposite. Now, you will see for every action there's an equal and opposite reaction. That's an old version of this, because remember, Newton didn't have all the same terminology that we use now. And I don't like that, because action and reaction imply changes in motion, or something happening, some action verb. It's a better definition of conservation of momentum, which we will get to later. But for now, I think, let's just say for every force, there's an equal and opposite force. And I mean, it's not wrong to say equal and opposite reaction. I just don't like it. Okay. Forces. Let's talk about forces and look at a free body diagram. So one of the things that we're going to do is to draw the forces on an object with a free body diagram. A free body diagram just says, okay, here's my object. I'm going to represent it as a dot, and then I'm going to draw all the vector forces acting on it. So in this case, I could have the weight, I could have the table, and then I could have some string maybe, or a push. Okay, so that's my free body diagram. We're going to draw all the vectors acting on the object. It can be a very useful thing, but when we see that, we are assuming that that whole object only exists at that one point for now. Now later, we're going to look at rigid bodies, where we do have to take into account where that force is applied. But for now, we're going to apply all those forces into just one point, and we're going to treat that object like this, as though it were just a single point in the middle. And that's a free body diagram. Now, we want to talk about the different kinds of forces. And in this case, let's talk about this one, weight. So the gravitational force, weight, I'm terribly sorry about that. The weight is equal to mg. And we sometimes just call that F. G is mg, like that. So this says that the gravitational interaction between the object and the Earth can be calculated by the mass of the object, and g is the gravitational field. Remember that g is a vector equal to negative 9.8 y hat, if I assume this is the y direction, which I don't always have to. If that's the y direction, negative 9.8 y hat, and it would have units of newtons per kilogram. And that is the gravitational field. So if I multiply that by mass, then I'll get units of newtons. And that is the gravitational force. It is indeed an interaction between the object and the Earth. All of the properties of the Earth are right there. And we will use a better model for the gravitational force later, but for now this is fine. It's always pointing towards the ground and has a constant gravitational field, so we can calculate the mass. If we know the mass, we can calculate the gravitational force. Now, let's just go ahead and apply this for a free-falling object, because it is important. Galileo showed this, right? If I have an object M, mass M, it has a free body diagram, I'd let it go, so it has a weight equal to mg. If I plug that into Newton's second law, it looks like this. F net is mass times acceleration. Well, the net force is only one. It's the weight. I'm just going to write that as the weight equals mass times acceleration. This is not negative. Okay, it has a negative y component, but we add up all the forces. So we have to include that like that. If I write this in the y direction, I can say F net y. Now it's a scalar value, and I do have a negative mg is the value of the y component of that. Negative mg equals may, and you'll notice here the mass cancels. So the acceleration of a free-falling object is negative g. That's what we had before. It doesn't matter what the mass is. I can take two objects of the same mass. If there's no other forces acting on them, they will have the same acceleration. Sometimes that's not true. If I take that piece of paper, which I already lost, here's another one, and let's do this, just to show you this little piece of chalk and my paper, they don't have the same acceleration. And we'll talk about that later, okay? But for now, let's just say free falling means the only force acting on it is the gravitational force. Now let's look at some other forces. I want to point out the difference. I'm going to write this here. Weight equals mg. This is what we call a calculated force. The book doesn't really talk about this, but it's important. Because I have an equation for it. I can just put in my values and I get the vector value of the force. But there are some forces, forces of constraint. So let me show you a force of constraint. Well, I'll tell you, the two that we're going to look at are tension and the normal force. So imagine that I put this block right there. Let's draw a free body diagram for this. Now, in this case, I know that the acceleration is 0 because it's just sitting there. So I can say F net. Oh, I said I was going to draw the diagram. So I know I have the weight acting down on it, and since the net force is equal to 0, because the acceleration is 0, there has to be another force acting on this, and that is the force from the table. I'll call that N vector. I know that looks like a Newton. That's the vector force N, which stands for the normal force. And in this case, in the y direction, F net y is going to be N minus mg equals 0, so N is equal to mg. So if I know the gravitational force, I can calculate the normal force. They have to have the same thing. Now, those are not equal and opposite forces. Those are not the Newton third law pairs that we talked about, because this is the table pushing on the block, this is the earth pushing on the block, so they don't have the back and forth that we had before. But now imagine over here that I push down with 10 Newton force. This is called that FP. And it's still at rest. In that case, I now have this. This becomes minus FP. So now N is mg plus FP. And what would happen if it didn't have the right normal force? What if this normal force is too high to balance out these? Well, then the block would accelerate up. That would be weird. If the force is too low, the block would accelerate through my hand. That would be weird. So in fact, this normal force is a force of constraint. That means there is no equation to calculate the normal force. There's no calculated version. You can't say the normal force equation is. Instead, the normal force applies whatever force it needs to prevent that block from coming off of the surface or going through the surface. In this case, normal means perpendicular, so the force is always perpendicular to the surface. We're going to look at later a force parallel to the surface, but for now, let's deal with that. So let's look at this case right here. Suppose I take my surface and I put I tilt it like that. I'm using an eraser right now. In this case, what would the free body diagram? Oh, actually, I'm going to let it slide. Let's let it slide because I don't want to have friction yet. So if I draw that diagram, there's something very important we can get from here. So here is the block, this angle theta. This comes up a lot, so it's important to look at it. Here's my block. Now, what force is acting on the block? There's the gravitational force. I'll just write that as W. And then the normal force is this way, because that's perpendicular to the surface. Now, if I want to write down Newton's second law here, I have to make a choice. If this block is accelerating down the plane, I want to do something that's going to make my life easier, and that's to do this. I'm going to call that the x direction. If I call that the x direction, then that's the y direction. So the x and the y direction are the domain of humans. We can do whatever we want. We made them. If you want to put the axis tilted down the plane, that's your decision. You're the human. And in this case, it's really good because if in this orientation of the axes, I have the block accelerating in the x direction, but not accelerating in the y direction. So I can say f net x equals max, f net y equals 0. It does not accelerate this way. If I put my axis this way, it's going to accelerate in both the x and the y direction. Now, here we can do something very useful. I know the acceleration is 0, so I can find the value of that force. So let's look at the values of forces in this direction. Here I have the normal forces in the y direction, and then I have part of the gravitational force in the x direction. And this angle right here is theta. So let me just show you how you can get that angle of theta with a little bit bigger picture here. If this is theta, and I have this, I want to find out that angle. Well, that's a right triangle. That's theta. This angle is the complement of theta, right? Because the angles in a right triangle have to add up to 180 degrees. So 90, this has to be this 90 minus this. Well, now I have another right triangle right there, so I have the complement of theta, and that's the complement of the complement of theta, which is theta again. So if I use it over here, I can now find the component of gravity in the y direction. It's going to be negative mg cosine theta, and that's 0. So this is a great example. Remember, we're finding components. We have to look at the picture. This is my adjacent side of the triangle. So if I take the cosine of the angle, it's going to give me the adjacent side. So I get negative mg cosine theta. So that gives me a value for n as mg cosine theta when I add it to both sides. So n is not always equal to mg. Okay, it comes up a lot. Be careful with that. We can also do the same thing in the x direction. Now I can find this component right here. Get mg sine theta is max. Okay, because that's my opposite side. Okay, we'll do some problems with that. But that's how we start. Now let's look at another calculated force. It's the tension in a string. So we're going to assume massless strings. We don't have to worry about the mass of the string. And tension is also a force of constraint. It will exert whatever force it needs in order to not break, not stretch. So I could have some block here, and I could have a string pulling that way and a string pulling that way. We'll call that T1. We'll call that T2. The only really thing that you need to know about the strings is that they can only pull in the direction of the string. Okay? They only pull this way. I can't pull that way. the string's tilted that way. They can't push. See? Try to push, what happens? It just collapses. Okay. So that's the tension. Let me give you a quick example of Newton's third law, because I don't feel like really addressed it quite well. Let's say I have two blocks, A and B, and let's draw, and they're sitting on a table, one on top of the other. And let's draw the force diagram for this one. This one's pretty easy. I'm going to write this as WB, and this is going to be the normal force, but I'm going to write it as FA pushing on B. So for block B, I can say F net Y is going to be FAB minus MBG equals 0. Now, if I draw the force diagram for block A, I'll do it to the side here. It's going to have the weight MAG. It's going to have the table, I'll call that F, table on A, and then it's going to have block B pushing down, FB pushing on A. So the weight of block B does not push on A. A lot of people do it that way because it looks that way, but it's not. Let's write down the diagram here, F net, the equation F net Y. For this equation, it's going to be F table pushing on A minus FB on A minus MAG equals 0. So yes, this is equal and opposite to that, but it's different forces. Make sure that in my diagram here for block B, they all are acting on B. On block A, they're all acting on A. Okay. And these two would be equal and opposite, but they're different forces. Okay, moving along here. Inertial frames. This one's complicated. It's a cautionary tale. Okay. So we would like to use what we call inertial reference frames. Let me show you a non-inertial reference frame. Here's an inertial reference frame, and I'll show you a non-inertial. Here's a person standing in an elevator, and then if the elevator's at rest, so I have the weight, and then I have the normal force. And those two are equal, because the acceleration is 0. But now what happens if the acceleration is up, if the elevator accelerates up? I don't know if you've ever been in an elevator, but when you push that button, you feel different. Does your weight increase when you feel that, when you push the button and it accelerates up? No, it doesn't, because this is the interaction between you and the Earth. In fact, what happens is the normal force increases and the weight stays the same, and that causes the person to accelerate. But this is what we call a non-inertial frame. Because if you are in this frame and you try to use Newton's second law and you try to measure everything with respect to the elevator, it doesn't work, right? Because you'd say, oh, well, the gravity is this force, the normal force is the normal force, right? Just like before, I'm standing there, there has to be some other force acting on me. And that's what it feels like. But it's not. And in fact, we don't like to deal with these reference frames that accelerate because they're very complicated. So just remember, we're going to try to think about, what if I had a window in the elevator and I could see it from outside? Oh my gosh, it froze. I'm just saying so that we'll do this. I think I'm just recording too much. Okay, so we're going to use inertial frames. Okay, I'm going to stop there. There is a section at the end about fundamental forces, but it's not super important. We're going to practice some problems, and hopefully I won't have video problems and I got talk all over me. Okay, that's good.